It is a fascinating journey, this path of knowledge, and the vehicle we ride is a science called chemistry.
Hello, I'm Roald Hoffman, and today we'll be looking at the fundamental forces behind the electron, and more specifically, electron levels. Did you know that all of the components of the world, all the birds, the buses, and the trees, are made up of electrons interacting? In fact, it is the interactions between these electrons that make up all of the chemicals of the world. If you remember from last episode, electrons are the very small, negatively charged components of an atom that orbit incredibly quickly around a dense, positively charged nucleus. Now, we're going to look at an experiment to more accurately illustrate this.
Hi, I'm Don Showalter, and today we're going to set pine cones on fire after soaking them in different solutions. We're going to soak them in KCl, NaCl, LiCl, calcium chloride, copper sulfate, copper chloride, and don't forget to replenish yourself after a long experiment. But I asked myself, what colors are these pine cones going to burn? I don't know. Only time will tell. The next step is to put each pine cone into its respective solution. Initially, we considered 2 pine cones, 1 cup. But we decided that just wouldn't work. So we're going to stick with the traditional 1 pine cone, 1 cup to conserve. All we got to do is plop them in. To combat the moisture from soaking the pine cones in different solutions, we place them in the oven. After a few minutes, they'll be ready to set on fire.
What are you doing, Dom?
Oh hey Dave, they were sizzling too much, so I'm just giving a good old flip.
After toasting the pine cones in the oven, the water has evaporated, but the ionic compounds still coat the surface of the pine cones. Now Nathan's gonna light the pine cones on fire, and we'll see what happens to the flame. But first, Nathan's gotta put on his safety glasses, courtesy of Safety Dave.
Thank you, Safety Dave. Now let's get started. After doing that once, I have to say the blue one's my favorite. I want to do it again. Blue. Now the red one was pretty cool too. Red. Blue, red, as said. Oh shoot! Fluorine, uranium, carbon, potassium. That's the wrong episode.
Safety Dave!
Thanks to Safety Dave. Thanks to Safety Dave, we're all safe. I was just having way too much fun. Now that's the #1 thing to remember in chemistry. Do not have too much fun.
And also, don't eat the yellow snow.
So we've seen a cool experiment. We have seen that pine cones coated in different ionic compounds burn different colors. But why? What is the chemistry behind it? To answer this question, we are going to have to take a look in the past and understand how electrons are organized in atoms. In 1752, the Scottish physicist Thomas Melville discovered the same thing we just did. Burning different compounds produced differently colored flames. Independently, it was discovered that when hydrogen atoms were excited, they emitted 5 distinct frequencies of light. These 5 frequencies averaged together to look a pinkish purple. In 1913, Niels Bohr looked at this evidence and believed that the current Rutherford's model did not explain why hydrogen emitted 5 different frequencies of light. In response, he created the Bohr model. The Bohr model is based on the theory of quanta. Quanta is the smallest amount of energy possible. Bohr applies quanta to his model by stating that, unlike the Rutherford's model, where the electrons are organized randomly in electron clouds surrounding a tightly compacted positively charged nucleus, electrons orbit the nucleus in different energy levels, which get increasingly far away from the nucleus. Applying this to the hydrogen light spectra, this would explain why 5 specific frequencies of light were emitted from the excited hydrogen atom. When excited, the heat energy bumps hydrogen electrons from its normal ground state to a higher energy level, farther from the nucleus. The electron then releases its gained energy in the form of light as it returns to its ground state. The farther that the electron jumps back to its ground state, the higher frequency the light is going to be. This is given by the equation H equals N nu, where E is energy in joules, H is Planck's constant, 6.626 times 10 to the negative 34th joule seconds, and nu is frequency in inverse seconds. Using this equation, if a certain element releases light that is 450 nanometers and has a frequency of 6.67 times 10 to the 14th inverse seconds, the energy of light is 1.06 times 10 to the negative 20th joules. This amount of energy can then be used to understand the distance that the electron jumps back to ground state, and therefore the electron configuration of a certain element. Although Bohr's model explains why hydrogen emits 5 distinct colors, it poorly explains the reasons why certain compounds burn certain colors. This is because Bohr was unaware of sublevels. Sublevels are levels within energy levels. The 4 sublevels are S, which holds up to 2 electrons, P, which holds up to 6 electrons, D, which holds up to 10 electrons, and F, which holds up to 14 electrons. The sublevels are organized in order by increasing distance from the nucleus in the pyramid of power. The pyramid of power dictates that the order is 1s, 2s, 2p, 3s, 3p, 4s, 3d10, 4p, 5s, and so forth, going upwards like this. The existence of sublevels complicates the emission spectra of more complex atoms than hydrogen. For example, looking at calcium-2+, which we used in our experiment, calcium-2+ has 18 electrons organized in sublevels and orbitals, which all interact with each other. These 18 electrons are jumping out of their ground state to different outer rings and then back down to emit lights of many different discrete frequencies. However, all of these frequencies average out to look orange. As you saw though, not all of the compounds burned orange. This is because since the electrons within different atoms are arranged in different orbitals, sublevels, and energy levels, on average, electrons of different elements are jumping different distances to return back to ground state, and thus releasing different frequencies of light. Looking at the 6 compounds we burned, going from left to right, on average, the electrons jumped an increasingly large distance as the frequency of light emitted increased. You can see it's going from red, orange, yellow, green, blue, purple, in increasing frequency. Chemists and physicists have run experiments similar to ours to try to determine which elements will burn which colors. They have since developed the Rydberg formula to generate possible wavelengths of light for given compounds. It's very complex and we're not going to go into it. You may ask, so we know that different compounds burn different colors, but is there any application to this besides burning pine cones? Well, yes, there is. Since every element has its own unique emission spectra, scientists can use this knowledge to identify compounds that compose an unknown material by comparing the two's emission spectra. This exact technique was used to discover helium in the sun. Hopefully now you have a better understanding of the chemistry behind burning pine cones.
The chemistry of electrons really fascinates me. There's so much to be learned here. In fact, the current theories are just that, theories. Our generation has managed to prove many things about the electrons, but there is so much to be learned, and it is up to you, the next generation, to prove whether or not we are right. Just think of the many wonderful things that have been developed thanks to an understanding of how the electron works. The powerful forces that fuel our spaceships, and the glowing neon signs that light our gas stations and strip clubs. With a better understanding of electrons, future generations can build better technologies to make the world a better place.